Okay, we're recording, in case you want to know. I know people are still joining, but I have to hit record first before I share the screen. Okay, looks like it's working now. But I will wait because I said 11:20, so I won't start until then. Well, you got a 10-minute break at the beginning, I guess. Okay, those of you just joining back, it looks like I was able to get the camera thing back on, but I said 11:20, so it's not fair for me to start until then. So I'll keep this screen here. Okay, yeah, anybody that I missed for attendance before, go ahead and put it in the chat and I'll get you. If you don't know what happened, you didn't miss anything, unless you're talking about, you know, my computer not working. I was missing something, so I couldn't get the shared screen working, but it looks like I'm back on. Okay, again, I won't start until 20 after, because that's what I said. It wouldn't be fair for me to start. Okay. All right, so everybody joining in, I'm just holding on until 11:20, since that's when I said I'd start. So it's not fair for me to start early, since some people heard me say 11:20. It wouldn't be fair for me to start before that. And I do see that it's 11:20 now. Okay, so I'll go ahead and start up again. All right, if you missed me for attendance, go ahead and put it in the chat. It is 20 after. I finally was able to get the screen share back, so I'll begin class now, 10 minutes late, but that's okay. That's to be anticipated, I guess, when you're teaching on Zoom. Okay, so we're 5.7 and 6.1. By the way, we're already recording. For anybody who's joining back, maybe you saw the message, but we're recording right now. Okay, so I did one problem from 5.7 last time, okay, which is the last section of chapter 5, and then we're on to chapter 6, which is on trig. Okay, again, not to worry if we quote unquote fall behind. That's why I have all these buffer days. So we'll see how it goes. Okay, so I did one problem yesterday from 5.7, and I'll try to do more. And you want to have your calculator handy. Okay, so get your calculator ready. Just very calculator dependent. And even when we get to trig, it's very calculator dependent also. All right. Exponential growth and decay is the topic. Here's the one formula. Put that on your formula sheet. N of t is n0 e to the kt. N of t is the new amount. N0 is initial amount. E is, you know, the base for natural logarithms. It's 2.718, so on. K is a constant. T is time. Okay, so problems generally start off with that. All right, so yesterday I did number 2. I want to at least do the evens for you. So let's go to number 8. And I guess I should do 18 for you. And then if I have time, I'll go back and do some of the odds, since you have the answers in the back of the book for the odds, okay? All right, so let's see what's happening for number 8. In the year 2000, the nations of Mali and Cuba had similar sized populations, Mali 11.2 million, Cuba 11.1 million. However, the relative growth rate for Mali was 3.1% per year, whereas that for Cuba was 0.7% per year. Okay, those are the Ks. They're giving you the Ks. Assuming exponential growth at the given rates, make projections for each population in the year 2015. Okay, so how do I do that? So question number 8. All right, so Mali, decay is 0.0031. That was given, 3.1% per year. So 3.1% is 0.0031. Cuba is 0.7% is 0.007. All right, maybe I'll just leave this at the top. N of t is N0 e to the kt. So for Mali, N of t is initial amount, and they said it's 11.2 million. So 11.2. Okay, now if it says 11.2 million, you don't have to put the 0.00000. I'm just going to put 11.2, and we know it means millions. That already means millions. Okay, that's allowed. E to the k 0.0031 t. And for Cuba, it's N of t. So Cuba's population, it says, was 11.1 million. E to the 0.007 t, right? So these are the formulas for the way that the population of Mali and the population of Cuba grow. Okay, so A, assuming exponential growth at the given rates, make projections for each population in the year 2015. So this experiment starts in the year 2000. So 2015 would be 15 years. So I just plug in 15. Okay. So for Mali, N of 15 is 11.2 e to the 0.0031 times 15. And the answer is going to be so many million. Okay, so I'll just punch that out. Okay, 11.2 e to the parentheses 0.0031 times 15. 11.73 roughly. (11.2 e to the 0.0031 times 15 is what I did over here. 11.73 million. And do the same thing for Cuba, it says. Its N of 15 is 11.1 e to the 0.007 times 15. And the answer is again so many million. Okay. So 11.1 e to the 0.007 times 15. Let's see. I made a mistake here. Mali should be 0.031. Yeah, sorry, 0.031. Anyway, Cuba, 12.33. Yeah, I goofed here. It's supposed to be 0.031 for Mali. Do that again. Point 0.031 times 15, so it would be a much larger number. 17.83. Sorry about that, I goofed. Okay. Yeah, some of you just joined. If you just joined, put it in the chat. You had internet connections. Welcome to the club. I had internet problems for the first 10 minutes. So from 11:10 to 11:20, I was just getting my computer to work, which I finally got. So you haven't missed much. All right, so I think this is correct now. 7.83 million, 12.33 million. Okay. B, when might the population of Mali reach 20 million? So the left-hand side, I put 20. The N of T is 20 for Mali. So the left side is 20 equals 11.2 e to the blah, blah, blah. So 20 equals 11.2 e to the 0.031 t. And again, I goofed here. Decimal point should be there. 0.031, that's 3.1%. Okay, so I solved this. Okay, divide both sides by 11.2, 11.2, that cancels out. 20 over 11.2 equals e to the 0.031 t. All right, do you remember how to get rid of the e? ln both sides, natural log. So these guys cancel out. ln of 20 over 11.2 equals 0.031 t. Divide both sides by 0.031. And the time is so many years. All right, so natural log parentheses 20 divided by 11.2 close parentheses divided by 0.031. 18.7 years. Okay. We have to give a calendar year, so we're going to approximate it to 19. Okay, so ln 20 divided by 11.2 in parentheses, ln 20 divided by 11.2 divided by 0.031. 18.7 rounds off to 19. Okay, now it says when means a calendar year after the year 2000. So the calendar year is 2000 plus 19, which is 2019. Okay, and then it says, what will the population of Cuba be at that time? So I go back to the original formula and plug in 19 for Cuba. Okay, so for Cuba, here's the formula, 11.1 e to the 0.007 times 19. (11.1 e to the 0.007 times 19). Okay, 11.1 second function e to the parentheses 0.007 times 19. This is what I'm punching in my calculator. 11.1 e to the 0.007 times 19. 12.68 rounded off. All right. So you see Cuba is growing much slower than Mali. Mali appears to be growing much faster. All right. Okay, so that's that one. And let's see. The only other even one was 18. So let's see what 18 is about. The following table gives a population size and relative growth rates for 3 states, Iowa, Arkansas, and Nevada. Use exponential models to project the population of each state in the year 2010. Listing results from largest to smallest. This order remained the same as it was in 2000. Okay, so from 2000 to 2010, that's 10 years each, right? So this is the N0. These are the relative growth rates. So you would have 0.0054 and 0.0137 and 0.0663. Okay, so I can't show you both the book and my work at the same time, but I'll just try to write what we had for each. Right, so in the language, they started with the year 2000, and we're looking at 2010. I'll show you that quickly again. So from 2000 to 2010 is 10 years. So in each case, I'm going to be plugging in 10 years. Okay, so for 18, Iowa, N of 10. So the number they put is 2926 e to the 0.0054 times 10, because the relative growth rate was 0.54. So that's 0.0054. Okay, and it's going to be so many million. 2926 e to the parentheses 0.0054 times 10. 3088. Wow. A little bit more than 3 million. Okay, then Arkansas, do the same thing, except their numbers are 2673 e to the 0.0137 times 10. And that's so many million. 2673 e to the 3065. 3.065. Okay, Nevada, however, is growing the fastest. So Nevada, N of 10, is its population was 1.998. Decimal point here, sorry. 1.998 e to the 0.0663 times 10. So I'm anticipating Nevada's growth rate to really make it zoom past the others. 1.998 e to the 3.88. Okay, so Nevada's population grows much more rapidly compared to what Iowa and Arkansas looks like. Okay, that's a 0 there. 3.065. Okay, so I showed you all the evens. Now I'll go back and do maybe some of the odds that are there and show you how to do those. Okay. Okay, so let's see. Go back and do number 1. Okay, number 1. At the start of an experiment, 2,000 bacteria are present in a colony. 2 hours later, the population is 3,800. Determine a growth constant K. Determine the population 5 hours after the start of the experiment, number 1. Okay. So use the formula N of T is N0 e to the KT. I plug stuff in. It says at the start, 2,000 bacteria. That goes here, N0. The new population is 3,800. That goes here. And the time is 2. So 2 goes here. So 3,800 equals 2,000 e to the K times, times 2, 2.0. 2.0. Okay, so divide by 2000, cancel. So 1.9 equals e to the 20k. How do you get rid of e? ln. ln 1.9 equals 20k, divide by 20. All right, so k is ln 1.9 divided by 20. And those of you that have a backwards calculator, you do the 1.9 first. So 1.9 and then ln, and then divide that by 20. So divided by 20. 0.03209 roughly. 0.03209 and some other stuff. If you want greatest accuracy, keep every digit. For now, we'll just go 5 digits, let's say. Right, so the formula is n of t is 2000 e to the 0.03209 t. Okay, then part B, determine the population 5 hours after the start of the experiment. I just plugged in 5. Okay, so this was part A. B, n of 5, 2000 e to the 0.03209 times 5, which is whatever. Okay, 2000, second function, e to the parentheses, 0.03209 times 5, 2348. If it's bacteria, you round to the nearest whole number. 2000 e to the 0.03209 times 5, 2348, rounded off. And then C, when will the population reach 10,000? So 10,000 is the left side. It's that n of t thing. Okay. So for C, 10,000 equals 2,000 e to the 0.03209 t. Solve for t. Okay, divide by 2,000. Divide by 2,000. 10,000 divided by 2,000 is 5. 5 equals e to the 0.03209 t. How do you get rid of the e? ln. And ran out of paper, so I got to go back up. So it's going to be ln 5 is equal to 0.03209 t. Okay. So let me write that up above.
Professor,
ln 5 is
where did you get 20?
209 t divided by 0.03209, 0.03209, 0.03209, cancel out. So t is going to be so many, and the time frame is days, wasn't it? No, hours. Sorry, yeah. So my answer is so many hours. All right, so let's see, ln 5. Okay, on this calculator, 5 ln, go backwards, and divided by what? 0.03209, divided by 0.03209, 03209 equals 50.15, looks like. Hours, so that's what, a little bit more than 2 days, 24 hours a day. Okay, Let's see. I messed up somewhere. Where did the 20 come from? It was 2. Okay. I have to find out where we're talking about here. Okay, I'm not quite sure where we were for the question. I mean, the concept is here. At least you got the concept. So if I screwed up a number, that's not a surprise. Let's see. I think this was 2000. Okay, I'm not quite sure where the mistake was, but hopefully you got the idea. The exponent on 1a. Ah, I see. It was 2, and this is supposed to be 2.0, not 20. Yeah, maybe that's where it fouled you up. Okay, so this should be 2 or 2.0. Yeah, that's a 2 and that's a 2.0, if that's what you mean. Right, thank you. Okay, so I think we're caught up. All right, then let's see, what time is it? Okay, so we've only done growth so far. I'm going to do decay. Decay is often like radioactive decay, or it could be population going down. Okay, so let's see situations like that. All right, so the problems at the end. So 25 to 33. Try some of those. Yeah, 25. The half-life of iodine 139 is 8 days. How much of a 1 gram sample will remain after 7 days? Okay, so this is radioactive decay. Okay, so let me put down the key piece of information there. So half-life of iodine 131 is 8 days. Okay, you have 1 gram. How much is left after 7 days? So it's almost a half-life. All right, don't use the 131. It names a certain isotope, and this is getting more technical than I think I need to, but don't use the 131. The name of the isotope, the name of the chemical is iodine 131. Okay, it's used for treatment of the pituitary gland, I believe, if you get enlarged thyroid, I take it back, enlarged thyroid. Okay, what is half-life? Half-life is a time needed for a substance to reduce to half its amount. Okay, half-life is a time, okay, a time needed to reduce to half the original amount that you have. Okay, it doesn't go in a straight line. Okay, so maybe I'll illustrate. So I'm taking a little time out, illustrate. So let's say we have half-life of 8 days. And it's different for different substances. So don't think that everything has a half-life of 8 days. No, some things have a half-life of many years. Some have a half-life of only a few seconds. Okay, so let's pretend we have, I'll go amount and elapsed time. So amount is in grams, time is in days. Okay, so for illustration purpose, suppose I start off with 16 grams at time 0. Okay, the half-life is 8 days. So that means after 8 days, I have half of 16, which is 8. Okay. The thing that's tricky for some students, though, is you might think, okay, after another 8 days, it's going to be all down to 0. It doesn't work that way for half-life. Okay, you take half of this amount. So half of 8 is now 4. Okay, and after another 8 days, that would be what, 24? You have half of that amount, which is 2. Get the idea? And another 8 days, 32, you have half of 2, which is 1. So that's the way half-life works for substances which decay in this fashion. Half-life is 8 days. All right, so first thing I got to do is figure out the decay constant. So start with n of t is n0 e to the kt. Okay, now, they told me we start off with 1 gram. So 1 goes here. The half-life is 8 days. So 8 goes here. 8 goes here. This is going to be 0.5, which is half of 1. That's the way it works. 0.5 equals 1 e to the k times 8. Okay, so one more time. It said we start with 1 gram. So it'll go down to half the amount. So half of 1 is a half, or 0.5, after 8 days. Okay, so let's solve for k. 0.5 equals e to the 8k. Knock out the e. ln. ln 0.5 equals 8k. Divide by 8. Divide by 8. Okay, so ln of 0.5. ln 0.5 divided by 8. Negative 0.086643. Something like that. ln of 0.5 divided by 8. Negative 0.086643. Okay. It should be a negative quantity. For substances that decay, the constant is negative. If it's a growth, the constant is positive. Decay, it's a negative. All right, so now I plug back in. N of t is N0 is 1. Well, if it's 1, you don't really have to write it, right? Because 1 times that is just that. I'll put it in just for completeness, but e to negative 0.086643 t. Again, you don't really have to write the 1. All right, then it says how much will remain after 7 days? I plug in 7. And if 7 is 1, okay, I'll put it e to negative 0.086643 times 7. And the answer is going to be so many. What do we do with grams? Yeah. All right, so I just punch it out. Second function, e to the 7 times the answer. 0.545 grams. And that kind of intuitively makes sense. The half-life was 8 days. So 8 days, you'd have exactly half. 7 days is not quite, so it should be a little bit more than 0.5. And it is, I see it's a little bit more than 0.5, 0.545, so not quite a half-life. So it does make sense. Okay. All right, so that's how that one works. I'll do another half-life type of problem for you. Go do 31. The half-life of plutonium-241 is 13 years. How much of an initial 2-gram sample remains after 5 years? Find the time required for 90% of the 2-gram sample to decay. Hint, if 90% has decayed, then 10% remains. Okay, let's get all that data down. And then maybe we'll break after that. 31. Okay, plutonium. I'll just put Pluto. 241. Don't use the 241 anywhere. It names an isotope, so to speak. Half-life 13 years. Okay, so you have 2 grams. How much is left after 5 years? So first I have to get the decay constant. So use our formula. N of t is N0 e to the kt. We start off with 2. After 13 years, how much is left? Half-life. Started with 2. You have 1. That's what half-life means, right? After 13 years, if I plug in 13, you have half the original amount. The original was 2, so I have 1. Divide by 2. 0.5 equals e to the 13k. ln 0.5 is 13k. Divide both sides by 13. So k is ln 0.5 divided by 13. Okay, if you're doing a backwards type of calculator, you have to do 0.5 first. So 0.5 and then ln. And then divided by 13, divided by 1, 3. Negative 0.05332, rounded off. It should be negative for a decay situation. All right, plug that back into K. So NFT is the original amount was 2, e to the negative 0.05332 t. Okay, so what did I do? I just replaced K with what it was equal to. There it is. That's a 0 there. Okay, now what else does it say? How much will remain after 5 years? I plug in 5. So n of 5 is 2 e to the negative 0.05332 times 5. Squiggly equal so many grams. Okay, 2. Second function, e to the parentheses, negative 0.05332 times 5. 1.53. See what I typed in. 2 e to the negative 0.05332 times 5, about 1.53. Yeah, all of that was part A. Sorry, I didn't put down A here. Part B. Okay, 31B. 90% decayed, so 10% remains. Okay, so I want 10% of 2. 10% of 2 is 0.2, isn't it? So I want to know when 0.2 grams is left. So 0.2 equals 2 e to negative 0.05332 t. Divide both sides by 2. 0.2 divided by 2 is 0.1. E to negative 0.05332 t. We've done this a lot of times now. How do you get rid of the e? ln. ln 0.1 is negative 0.05332 t. Divide both sides by negative 0.05332, and then we're done. Negative 0.05332. And my units this time are years. Okay, so you can have any unit of time. They could give you seconds, minutes, hours, days, years. It's fine. Okay, so ln 0.1 divided by negative 0.05332. 43.18. ln 0.1 divided by negative 0.05332. 43.18 years. So 43.18 years. And that'll do it. All right, folks, I am finished with 5.7. In fact, I'm totally done with chapter 5. So the next exam will cover chapter 5 and 6. Chapter 6, as you can see, there's only 4 sections. But again, I'm definitely moving the test for now back to Thursday, the 18th. Okay, so that's what we're aiming for. So after the break, we're going to get started with some trig 6.1. Okay, all right, so we'll break. And let's see, 12:10 seems to be a good normal stopping time. Okay, so break until 12:10, and I'll put that in the chat also. All right. Okay, folks, we're going to pick up again. So we are done with chapter 5. Starting chapter 6. So most of the rest of the class is on trigonometry, on trig. This is trig, this is trig, this is trig, this is trig. I believe this is also trig. There's still some sections that are not trig, but we're starting trig now. I know some of you have some trig background, some of you have absolutely none. When I'm speaking, I'm going to be speaking assuming you have no trig background. Okay, that's in order to be fair to everybody. So those of you that have some trig background, you've got a little bit of an advantage. But of course, I have to pick up everybody who's never had trig any time in their lives before. Okay, so I will be lecturing assuming you've never had trigonometry in the past. Okay, again, the next exam would cover chapters 5, for which I'm now done, and 6. And that will now be on Thursday, the 18th. Okay, so we're on to 6.1. Okay. If you've heard of SOHCAHTOA before, that's basically what this topic is right now in 6.1. So introduction to trigonometry using right triangles. Okay, so on page 422, here's a basic picture. Now, some of you don't need to take any notes on this because you already know it forward and backward. Some of you, this is the first time you've seen it, you have no idea what's going on. Okay, so first, here are the names of the 6 trig functions and their abbreviations. Cosine, sine, tangent, secant, cosecant, cotangent. Those are the 6 trig functions and their abbreviations, as you can see there, COS, SIN, TAN, SCC, CSC, COT. Okay, this is on page 422. Now, most of the time we'll spend on cosine and sine and tangent. We don't spend that much on secant, cosecant, and cotangent, except they're there. Okay. Now, other thing you want to know is right now we're doing right triangle trigonometry, which means there's a right triangle. What's a right triangle? There's a right angle. Okay. If you're given an angle, this is the Greek letter theta. It's that funny looking thing there. That's the Greek letter theta. It's usually meant for angles. Okay, so 6.1, introduction to trig. This is the Greek letter theta, 0 with a little mark in it. It's often used for an angle. All right, so with respect to angle theta, if you go across over here, the opposite side, this is called the opposite side, which kind of makes sense, OPP for short. The side next to it is the adjacent side. I will normally abbreviate with ADJ. And we have the hypotenuse. The hypotenuse is always opposite the 90-degree angle. So if you're given an angle theta in a right triangle, now this has to be a right triangle. If you don't have a right triangle, none of this applies. But there's an opposite side, the adjacent side, and the hypotenuse. Now, at first glance, you might say, oh, wait a minute, there's 2 sides that could be adjacent. It's this one and this one, which is true. But we already have a name for this one, the hypotenuse, right? So the adjacent side is a side next to the angle, which is not the hypotenuse, okay? Because hypotenuse already has a name, hypotenuse. Okay, so the hypotenuse, which you know from your earlier geometry, no doubt, is always opposite the right angle. So the other side, which is next to the angle, that's the adjacent side and the opposite side. Okay, now with that, we have all of these definitions. Okay, for those of you who know SOHCAHTOA, it boils down to SOHCAHTOA. I'll give you SOHCAHTOA in a second. Okay, so cosine is the adjacent side divided by the hypotenuse. Sine is the opposite side divided by the hypotenuse. Tangent is the opposite side divided by the adjacent side. These 3 are correct. There's nothing wrong with them, but to me, that's more stuff that you have to memorize unnecessarily. Okay, I think it's easier if you just think in terms of reciprocals, and I'll give these to you in just a bit. Okay, and again, you have a little bit of an advantage because I'm letting you have a cheat sheet. If we were meeting on campus face to face, I wouldn't give these to you. You'd have to memorize them, although a lot of you already memorized SOHCAHTOA, as I said in these. So you may put all of this on your cheat sheet if you want, but that takes up a lot of space. A lot shorter is SOHCAHTOA. Okay, and even when we were meeting on campus, I wouldn't let you write down SOHCAHTOA, but it's pretty easy to memorize. So I'll give you SOHCAHTOA. And now some of you are saying, you keep saying SOHCAHTOA. What's SOHCAHTOA? I'll tell you shortly. Okay, again, I'm going to speak assuming you've not had any background in trig to catch every student. And then these are the reciprocal functions. So I'll give you the reciprocal functions. Okay, so here is SOHCAHTOA. So what in the world is SOHCAHTOA? So first, let me draw a right triangle. Here's theta. You say, can theta be over here? Yeah. Theta is never the 90-degree angle, though. Okay, so this is the hypotenuse. I'll abbreviate with hype. This is the adjacent side. I'll do ADJ. And this is the opposite side, OPP. It gets too tiring to keep writing HYP, OTE, and USE, and ADJ, ACENT, and OPP, OSITE. So we'll just give 3-letter abbreviations. Okay, adjacent, opposite, hypotenuse. Okay, so what is SOHCAHTOA? SOHCAHTOA. Okay, so SOH, sine of theta, is the opposite over the hypotenuse. CAH, cosine of theta, is the adjacent over the hypotenuse. TOA, tangent, is defined to be the opposite over the adjacent. Okay. Now, what about the other 3? Secant, cosecant, cotangent. They are just reciprocals. Okay. So what they have here is correct. You don't really need it if you just think in terms of the reciprocals. So cosecant, secant, cotangent. They are reciprocals of these 1 over something. Okay, which one's which? Again, if we were meeting face to face, I would make you memorize it. I'll go ahead and give you the memory tricks, but you could put this on your cheat sheet theoretically. Well, to me, the easiest one is tangent. Can you guess which would be the reciprocal of tangent? Cotangent. Very logical, right? Okay. And now the only things you have are sine and cosine for cosecant and secant. Okay, here's the way I memorize it. If one function has a co, the reciprocal does not have a co. Okay, by that I mean cosecant, there's a co. So the reciprocal does not have a co, sine. Okay, on the other hand, secant doesn't have co, right? Cosine. Okay, again, because of the pandemic and we're meeting virtually, you can have your cheat sheet, but just in case you have to memorize it. And by the way, maybe, one of these days we're back on campus as quote unquote normal, and then your teacher might make you memorize all this stuff. So yeah, it's nice if you already have it memorized eventually, but here we go. These are reciprocal functions. So cosecant is the reciprocal of the sine. Secant is the reciprocal of the cosine. Cotangent is the reciprocal of the tangent. One function has a co, the other does not have a co. All right, so what is all this about, the secant, cosecant, cotangent? Well, since cosecant is the reciprocal of the sine, you could say cosecant is what? Hypotenuse divided by opposite, right? And likewise, you could say secant is the reciprocal of the cosine, so it's hypotenuse over adjacent. And cotangent, you could say, is adjacent over opposite. Again, you don't really need it. If you just go with this and just flip them, as the case may be. All right. That's that. That's the way it works. So, simple example, page 425. 3, 4, 5 triangle, and you see theta. So cosine is adjacent over the hypotenuse, 4/5. 4 divided by 5. Sine of theta is opposite over hypotenuse, 3/5. Tangent is opposite over adjacent, 3/4. And just flip them for the reciprocals. Just know which is which. Okay, cosine, there's a co. Reciprocal does not have a co. So secant, yeah, again, I don't really think you need all this. Just flip it, 5/4. Sine, the reciprocal sine does not have a co, so reciprocal is cosecant. Just flip it, 5/3. And usually students don't have any trouble with tangent, cotangent. It's kind of obvious. So flip tangent, 3/4, 4/3. That's it. Okay, now, they may not give you all 3 sides. If they only give you 2 sides, you can use a Pythagorean theorem, right? A squared plus B squared equals C squared. So let's say they give me a picture like this, right? 1, 3, hypotenuse. Oh, well, they don't give me the hypotenuse. Well, just do your A squared plus B squared equals C squared, right? 1 squared plus 3 squared equals the hypotenuse squared. 3 squared is 9. 1 squared is 1. 9 plus 1 is 10. So H is the square root of 10. And then you can do your stuff after that, right? As you can tell, sometimes the numbers aren't nice. You get some square roots, right? So 3 over radical 10, 1 over radical 10, and so on. Okay, so if they give you 2 sides, you can always figure out the third. Is that right? Okay, special triangles. 30, 60, 90 triangle. They say 30, 60 right triangle. Well, that means one of us with 90. 30, 60, 90. Okay. So there's a nice property right there. It says in theorem. See, what's a theorem? It's a provable statement in mathematics. You don't really have to know it though. In a 30, 60, 90 triangle, the length of the side opposite the 30-degree angle is half the length of the hypotenuse. Maybe you had that in high school geometry. The side opposite the 30-degree angle is always half the hypotenuse. Meaning if this is x, this is 2x. Always. Now you can do some Pythagorean theorem and show that this one is x radical 3. Okay, so that leads to these following conclusions. And again, if we were meeting on campus, you'd have to memorize these, but for now you can put it on your cheat sheet. So cosine of 30 is adjacent over hypotenuse, so it's x radical 3 divided by 2x, radical 3/2. Sine of 30 degrees, opposite over hypotenuse, x divided by 2x, 1/2. Here's a tangent of 30 degrees. And some things you'll notice, sine of 30 degrees is the same as the cosine of 60 degrees. Likewise, cosine of 30 degrees is the same as the sine of 60 degrees, radical 3/2. Okay, which kind of makes sense because if you look at the sine of 30, you're doing opposite over hypotenuse, x over 2x. Cosine of 60 degrees is adjacent over hypotenuse, but that's still x over 2x, right? That's always going to happen, right? So sine of 30 equals cosine of 60 and so on. Okay, the key items that I think you should know are this one and this one. You can derive the rest. Okay, but cosine of 30, radical 3/2. Sine of 30 is 1/2. Okay, and these two match. These two match. In fact, why don't I just write it in my book? Sine of 30 is the same as cosine of 60 degrees. Cosine of 30 is the same as sine of 60 degrees. You can put these on your cheat sheet if you wish. Okay, for 45, 45, 90 triangle, sometimes called an isosceles right triangle. Did you ever have isosceles right triangles in high school geometry maybe? X, X, a little bit of Pythagorean theorem, this would be X radical 2. Okay, so by using the Pythagorean theorem, you could show that this is X by X radical 3 and 2X. This is X, X, X radical 2. Okay, so that leads us to the following. Cosine of 45 degrees, okay, is adjacent over hypotenuse. So adjacent is X divided by X radical 2. Radical 2 over 2. Sine of 45 degrees is also radical 2 over 2. It was opposite over hypotenuse. What's opposite to 45-degree angle? Well, it's also X divided by the hypotenuse, which is X radical 2. So you get the same thing. The tangent was X over X, which is 1. Okay, so here's a nice little table. And if you want this table, you can have it. If we were meeting on campus, I'd make you memorize it. Table 1 on page 428. Sine of 30 degrees, cosine of 60 degrees is a half. Sine of 60 degrees is the same as cosine of 30 degrees, radical 3 over 2. Okay. I don't think you have to worry about knowing these that well. It's just going to be the ratio. But this is worth knowing. The tangent of 45 degrees is 1. Okay. Both sine and cosine of 45 degrees is radical 2 over 2. Again, you may put it on your cheat sheet, but if we were meeting face to face, I'd make you memorize it. Okay. Okay. We can get started with some of these. Okay, so I won't go too much longer. I'll do a few, then I'll have you do one in class. You put it in the chat, and then that'll be it. Okay, so we're on this side. You can see we're really progressing because I'm finished with this side of the paper. So now we're on this side of the paper, although it is more than half, but still. 6.1, 1 to 45 odd. All right, so they give you this picture. Okay, this is the Greek letter beta. So when you take trig, after a while, you learn the Greek alphabet. Okay, give the 6 trig functions of theta and beta, and if there's a radical, rationalized denominator. Okay, so page 429, 6.1. Question 1. Just do a quick drawing here. They go 8, 17, 15, beta, theta. Okay, so maybe just a quick timeout and a little bit of Greek. So this is alpha, first letter in the Greek alphabet. The funny looking B is beta, second letter in the Greek alphabet. And by the way, this is where we get our English word alphabet. We say alphabet. Okay, alpha is the first letter in the Greek alphabet, beta is the second letter, and you put them together, and that's how we use our English word alphabet. Alpha, beta. Okay, gamma looks like this. It's the third letter in the Greek alphabet. Okay, it's the equivalent of our C, I guess. Okay, we have a lot more. This is theta. These are often used for angles. Okay, so this is just some of the Greek alphabet. We'll get more. Well, you already know pi, obviously. All right, pi is actually a Greek letter, that funny symbol. But if you know Greek, that's the Greek letter pi. Of course, we use it for 3.14, blah, 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 right? So alpha, beta, gamma, theta. All right. So come up with the 6 trig functions of each angle. In this particular case, it says. All right, so let's use theta. So let's do our SOHCAHTOA. SOHCAHTOA. So sine theta is a fraction. Cosine theta is a fraction. Tangent theta is a fraction. Okay, so sine is opposite over hypotenuse. So let's look at theta. Opposite, 15. Hypotenuse is 17. So 15 over 17. Cosine is adjacent over hypotenuse. Ka, adjacent over hypotenuse. So this is the adjacent. And you may say, well, can't 17 be the adjacent? Yeah, but this is already the hypotenuse, right? So since we already called it the hypotenuse, this is the side that's adjacent because it's not the hypotenuse. So adjacent over hypotenuse, 8 over 17. TOA, tangent, opposite over adjacent. Opposite is 15, adjacent is 8. Okay. And then the reciprocals. And sometimes it's easier to get the reciprocals if you line it up right here, then you can tell, you just flip it. So reciprocal of sine, hint, there's no co, so co-secant. Reciprocal of cosine, there's a co, so reciprocal doesn't have a co. And there's really usually no problem for tangent, tangent, cotangent, right? And just flip these guys. So 17 over 15, 17 over 8, 8 over 15. That's all there is to it. Okay, notice we're actually not even finding theta yet. We will be able to learn the angle, but I haven't been able to establish, is this a 50-degree angle or 62-degree angle or whatever? We'll figure that out. But right now, even though we don't know the actual angle, we can find all these things. All right, it says the same thing about beta now. So sine beta, cosine beta, tangent beta, fraction, fraction, fraction. And usually once you have this, then, you just flip these. Okay, with respect to beta, okay, sine is opposite over hypotenuse. So opposite this time is 8, hypotenuse is 17. 8 over 17. Cosine beta, ka, adjacent over hypotenuse. So adjacent, is it 17 or 15, the adjacent? This one's the adjacent. This one's already the hypotenuse, right? So 15 over 17. Tangent, opposite over adjacent, 8 over 15. Okay, and before going on, you may notice sine of theta is the same as cosine of beta. That will always be the case for these kind of problems. And look at cosine of theta is the same as sine of beta. Okay. So usually once you have the cosine of one, you automatically have the sine of the other angle and vice versa. All right, and then just flip these guys. So cosecant beta, secant beta, cotangent beta. Flip, flip, flip. So 17 over 8, 17 over 15, and what, 15 over 8? Okay. All right. So I'm not going to go that much longer, and then I'll have you try one. Okay. Number 5, they don't give me a picture, so draw the picture. And they only give me 2 sides, so you can figure out the rest, right? Okay, so triangle ABC and angle C is 90 degrees. Okay, so C, A, B. Okay, it says AC is 3, BC is 2. Okay, AC is 3, BC is 2. All right, so I have to figure out the hypotenuse. Okay, so I'll call it X. Okay, so I use my A squared plus B squared equals C squared, Pythagorean theorem, right? 2 squared plus 3 squared equals X squared. Okay, I'm sure you've all seen the Pythagorean theorem. If not, a quick timeout. Review Pythagorean theorem. Pythagorean theorem, right? If you have a right triangle, A, B, C, C being the hypotenuse, then A squared plus B squared equals C squared. Is that right? So let's use that here. 2 squared plus 3 squared is X squared. 4 plus 9 equals X squared. X squared equals 13. So X is the square root of 13. And these are all distances, so you don't need to worry about plus or minus. Okay. All right, so I found this to be radical 13. All right, so what do they want? Cosine A, sine A, tan A. Okay. So cosine of angle A, ca, adjacent over hypotenuse. So adjacent is 3, hypotenuse is radical 13. Okay. And they say rationalize the denominator. Remember rationalizing the denominator in algebra? Multiply top and bottom by radical 13. And you end up with 3 radical 13 over 13. Although in my opinion, this isn't much better than this. I like that better. There's more stuff that you have to write here. But anyway, be that as it may. Okay, then they want sine of A. So sine is so opposite over hypotenuse. So angle A, 2 over radical 13. And do the same thing. Radical 13 over radical 13. 2 radical 13 over 13. Tan A, so ca toa. Toa is opposite over the adjacent. So opposite, adjacent, 2/3. Okay. Now, strangely enough, for part B, it asks for secant, cosecant, and cotangent of B, not cosine, sine, and tangent. But we have to figure out cosine, sine, and tangent of B anyway. Okay, although it shouldn't be that hard. So this is part A. Part B, let's just find all these. Cosine of angle B. Cosine is adjacent over hypotenuse. So adjacent over hypotenuse, 2 over radical 13. I'm not going to rationalize this denominator because I'm going to have to flip it in a second anyway. Sine of B, so that's an O there. Opposite over hypotenuse, 3 over radical 13. Tangent, TOA, opposite over adjacent. So opposite over adjacent, where'd it go? Would be opposite over adjacent, 3 over 2. And just as we said before, that is the same as that, and that is the same as that. Okay. In the original problem, it asked for the reciprocals, though. If you look at number 5, they asked for secant, cosecant, and cotangent. So secant is a reciprocal of the cosine. Radical 13 over 2. cosecant is the flip reciprocal of this. Radical 13/3. And cotangent of B, flip 3/2, 2/3. That's it. All right, so that's what we're up against for this section. Okay, we have a lot more to do, but I can save that for tomorrow. Okay, I'm done, folks. Any questions? Otherwise, I'll give you something to do in class, and then we'll call it a day. So either unmute yourselves or put it in the chat. Okay, if you have the book, you can just look off the book. If you don't have the book, then get your cell phone out. Okay, I want you to do number 2. Okay, only give me sine, cosine, and tangent of theta. Okay, so number 2, sine, cosine, and tangent of theta. Looks like you've got 20, 21, and 29. Okay, so number 2, sorry, I can't write it. Again, just sine, cosine, tangent of theta. Don't do the beta up there. Okay, I'll hold this for another 30 seconds maybe. Okay, problem 2, 20, 21, and 29. Give me sine, cosine, and tangent of theta. Use the SOHCAHTOA. Type it in the chat, and then you're done, and I'll see you tomorrow. Okay, again, just sine, cosine, tangent of theta. Okay. If you missed something, maybe I'll type it in the chat also for those of you who didn't get that. Okay, I'm going to make this disappear in another few seconds. So if you haven't gotten number 2 yet, please get it. Sine, cosine, tangent of theta. I can't type theta, so maybe I'll type THETA in the chat. Okay, so I'll make it disappear. And when you type it in, you can leave. All right, so I'll stop the share. And I'll type it in the chat also. Okay, so there it is. Find sine, cosine, and tangent of theta. Okay, if you have any questions, you can ask Star or me. And otherwise, you're done. We'll see you tomorrow. Okay, I'm going to stop the recording also. No need to record anymore.